we present just round. Quantized observation spaces enable memory-efficient learning of dynamic locomotion. Deep reinforcement learning remains one of the most powerful tools for synthesizing complex robotic behaviors, such as learning to solve a Rubik's Cube using a dexterous robotic hand, enabling robust quadrupedal locomotion in under 20 minutes using hundreds of parallelized rollouts, and teaching a minotaur to walk using experience collected on device and in the real world. Despite these advances, robot learning remains expensive, both in terms of compute and memory costs. This poses a challenge for the next generation of field robots, for example, search and rescue and space exploration, that will need to learn and adapt on the fly while being limited to either onboard compute and memory budgets or bandwidth-constrained network connections to the cloud. In this work, we begin to address this issue through observation space quantization. Within deep reinforcement learning, the overall memory footprint is generally dominated by either the on-policy rollout or off-policy replay buffer. We show here that in two recent state-of-the-art learning papers, these buffers account for over 95% of the total system memory footprint. Moreover, just the observations stored within those buffers alone account for over 90% of the total footprint. To save on space, previous works often reduce the maximum buffer size at the cost of model performance. In this work, we propose an alternate approach, observation quantization. In mathematics or signal processing, quantization, often synonymous with discretization, is the process of mapping a continuous series or signal to some discrete space. In the digital world, quantization usually refers to mapping a larger data type to a smaller one. This is especially useful in deep learning, where quantization has been applied to reduce model sizes while preserving learning performance. Recently, quantization has also been applied to deep reinforcement learning, specifically through model compression. To the best of our knowledge, however, quantization has not been explicitly proposed to compress observation spaces within reinforcement learning. This is the subject of our work. Generally, in state-based or proprioceptive control, an observation is a vector of 64-bit floats representing the internal state or external forces acting on a robot. The first step in our quantization scheme is to apply a clamp operation, which takes as input a 64-bit float and clamps the output between two bounds. Just looking at the integer component returned, we see that we can quantize a clamp -127 to 127 operation into 8 bits, 1 for the sign and 7 for the positive integer component. Next, we apply a round operation, which rounds a 64-bit float to a fixed number of decimal places. In this case, because we are keeping only one decimal place, we can encode this with 4 bits. The result of both the clamp and round takes a 64-bit float and compresses it to a 12-bit number. This compressed representation can then be saved in order to reduce storage costs. We evaluate our quantization approach on 4 simulated robotic walking environments. Our full source code, along with examples, can be found at the given link. First, we show convergence results across all 4 environments using PPO and SAC with and without observation space quantization. We average results across 10 random seeds and find that convergence is not substantially impacted by our quantization. Qualitatively, we see that the rollouts between the baseline and quantized agents do not differ much. In fact, in these PPO rollouts, the quantized agent, right, appears to survive longer. For SAC, both ANT agents act almost identically. And even in the more challenging humanoid environment, both SAC agents perform similarly. In terms of memory savings, we compute the total memory requirements of PPO and SAC, two state-of-the-art learning algorithms, both without and with observation space quantization. We break down the memory usage between the model black and buffer blue. We see that overall memory costs decrease by as much as 4.2 times with quantization. Finally, in our ablation study, we compare learning curves of SAC on the humanoid environment, both with quantization, solid lines, and without dashed, while adjusting the buffer size. We color coordinate by total memory usage and find that when holding memory footprint constant, the quantized agents converge to significantly higher rewards than their unquantized counterparts. And indeed, when we hold buffer storage size constant, we see that quantized agents perform significantly better. Here, the quantized agent is on the right. Thank you.